Hello learners, I am Dr. Subodh Kesharwani, working with Indira Gandhi National Open University in School of Management Studies. The topic which I am going to talk today is theory of testing hypothesis. In our preceding sessions, when we have started this talk, we were more focusing on sampling and hypothesis. We have given a glimpse about hypothesis, but now we are focusing more on how we are going to test the hypothesis. So this is a very important block because the whole statistics revolves around the testing and execution, and whatever the tools and techniques you have applied as far as the statistical techniques are concerned, now the time had come where we are going to test these hypotheses and able to know what our respondents have reciprocated and how we are going to put it in the final shape and get the results thereof. So anyway, we are going to talk about more about the sampling and hypothesis in our preceding session, and random sampling and statistics is something which is a very routine affair. So statistics derive its power from random sampling. The argument is that random sampling will average out the differences between two populations, and the differences between the population seen post-treatment could be easily traceable as a result of the treatment only. Obviously, life is not simple. There is little chance that one will pick random samples that results in significantly same populations. So even if they are the same populations, we can't be sure whether the results that we are seeing are just one time or rare events or actually significant, that is regularly occurring events. So anyway, statistical hypothesis, if we are going to talk about, a statistical hypothesis is an assumption about the parameter of the population or the nature of the population. For example, the population mean is mu equals 25. The average weight of students of college A and college B are same. 20% of the students of a college are non-vegetarians. The given population is a binomial population, are some of the hypotheses. So we have already talked about all these probability distributions, either it could be the binomial or Poisson or whatever it could be. We have very closely talked about all those things. So now we are just concentrating on the theory of the test of hypothesis, and during this course of discussion you will find out that we are going to talk about certain tests which are there. Either it could be the type 1, type 2 error, or the one tail, two tail test, or the T test, Z test or F test, whatever it could be. We will gradually go into the depth of all these things and then finally recapitulate what exactly we have done and then try to wind up the whole process. So anyway, at the x-axis we have independent variable, at the y-axis we have dependent variable, and we have the matrix which talks about nominal interval and then nominal interval. If the case is nominal, then what is going to be happen, that considers the distribution of one variable across the category of another variable, and you will find out that we are using a lambda over here. So anyway, if we are going to test the differences between the two groups, that consider the difference between the mean of one group on a variable with another group, and both are, one is interval, other is nominal, then the confidence intervals T test is going to apply. So anyway, we are going to talk more about all those things and in a coming discussion, and we will see that how the things are going to be changed. So when we are going to talk about this interval and nominal, where dependent variables are interval dependent variables, and we have nominal independent variables. So is one group scoring significantly higher on average than another group? Is a group statistically different from another or on a particular dimension? Is group A means higher than the group B? And do people living in rural communities live longer than those in urban or suburban areas? Do students from private school perform better in college than those from public high schools? Is the average number of years with an employer lower or higher for large firms over 100 employees compared to those with fewer than 100 employees? So these are the the statements which used to come. And hypothesis testing is the art of testing. If we go into the backdrop of this hypothesis testing, we come to know that hypothesis testing is the art of testing if variation between the two sample distributions can be explained through random chance or not. If we have to conclude that two distributions vary in a meaningful way, we must take enough precautions to see that the differences are not just through random chance. At the heart of type 1 error is that we don't want to make an unwarranted hypothesis, so we exercise a lot of care by minimizing the chance of its occurrence. So testing hypothesis is bifurcated into different segments. Statistical hypothesis testing, a procedure that allows us to evaluate hypotheses about population parameters based on sample statistics. And if we talk about research hypothesis, which can be considered as a alternative hypothesis, a statement reflecting the substantive hypothesis, it is always expressed in terms of population parameters, but its specific form varies from test to test. So null hypothesis, a statement of no difference which contradicts the research hypothesis and is always expressed in terms of population parameters. So there are 5 steps to hypothesis testing: making assumptions, number 1, stating the research and null hypothesis and selecting alpha, selecting the sample distribution and specifying the test statistics, computing the test statistics, making a decision and interpreting the results. So hypothesis testing, if you are going to talk about, is a process that uses simple statistics to test a claim about the value of a population parameter. So for example, an automobile manufacturer advertises that its new electric car or a hybrid car has a mean mileage of 50 miles per gallon. To test this claim, a sample would be taken. If the sample mean differs enough from the advertised mean, you can decide whether to reject the claim or fail to reject the claim. So if we go into the backdrop, statistical hypothesis is a statement of claim about a population parameter. Need a pair of hypotheses, the null hypothesis that represent the claim, and the other is alternative hypothesis. So if null hypothesis rejects, automatically the alternative hypothesis is going to be accepted, or vice versa, whatever the case could be. So we have to define the parameter, use mu for the true population mean, use P or rho for the true population proportion, do not use x bar and P. So now when we are going to state a hypothesis, we have very easily seen that in a figure that a statistical hypothesis that contains a statement of equality, that is equal symbol and denoted by HO0 or HO, read H sub 0 or H naught. So it means that and when you are going to talk about the alternative hypothesis, a statement of inequality as greater than or equal to or less than and denoted by HA, H1 and read as H sub A. So what we have observed that that we have null hypothesis, we have alternate hypothesis, and whenever we go for any statement or theory of testing, we have a pair of null and alternative, and these are known as a complementary statements also. So if one is not true, is true, other is false. If other is false, one is true. So to write the null and alternative hypothesis, translate the claim made about the population parameter from verbal statement to a mathematical statement, then write its alternative. And so HO, which is null hypothesis and is denoted by mu equals to K, and HA, which is denoted by H, this hypothesis, alternative hypothesis, is denoted by mu greater than K. So this is the way, and if mu is equal to K, that is null hypothesis, mu is equal to K, alternative hypothesis, mu is less than K. So here what happened, that hypothesis mu equals to K and null hypothesis alternative mu is unequal to K. So you always assume the null hypothesis, that is mu equals to K or null hypothesis equal to K is true, and then examining the sampling distribution on the basis of this assumption. So this could be the modus operandi by which we are going to do that. And stating the null and alternative hypothesis, write the claim as mathematical sentence, state the null and alternative hypothesis. For example, a university publicized that the proportion of its students who graduate in 4 years is 82%. So alternate null hypothesis is denoted by HO, and P is equal to 0.82, which is an equality condition claim. And when we exactly go into an alternative hypothesis, P is unequal to 0.82 complement of null hypothesis. So where P is the true proportion of students who graduate in 4 years. So write the claim as a mathematical sentence, state the null and alternative hypothesis. We can take another example. A water faucet manufacturer announced that the mean flow rate of a certain type of faucet is 2.5 gallons per minute. Our water pressure is low. So mu equals to 2.5 gallons per minute. That is claim, and mu is less than 2.5 gallons per minute. So where mu is the true mean of the water flow rate. So what we have observed that these are called the null hypothesis and alternative hypothesis. Now the directional test is there. So when a research study predicts a specific direction for the treatment effect, increase or decrease, it is possible to incorporate the directional prediction into the hypothesis test. The result is called a directional test or a one-tailed test. A directional test includes the directional prediction in the statement of the hypothesis and in the location of the critical region. So, for example, if the original population has a mean of mu equals to 80 and the treatment is predicted to increase the scores, then the null hypothesis would state that after treatment, alternative null directional test. For example, if the original population has a mean of mu equals to 80 and the treatment is predicted to increase the scores, then the null hypothesis would state that after treatment mu is less than or equals to 80, there is no increase. So in this case, the entire critical region would be located in the right hand tail of the distribution, because large values for m would demonstrate that there is an increase and would tend to reject the null hypothesis. So to define a statistical test, we choose a statistics called the test statistics, divide the range of possible values for the test statistics in two parts, the acceptance region, the critical region. So and to perform the statistical test, we collect the data, which we have already covered in our preceding session, the way of collecting the data, compute the value of the test statistics, make the decisions. If the value of the test statistic is in the acceptance region, we decide to accept HO. If the value of the test statistics is in the critical region, we decide to reject HO, that is null hypothesis. So if the test statistics fall in some interval which support alternative hypothesis, we reject the null hypothesis. The interval is called rejection region. So all these, the process is called the critical region. So it test statistics falls in some interval which supports null hypothesis, we fail to reject the alternative hypothesis. The interval is called acceptance region. So the value of the point which divides the rejection region and acceptance one is called critical value. So if you see this particular image, I think this particular image is quite useful as far as learning is concerned, as far as finding out the critical region is concerned, or the accepted region or the rejected region is concerned, is quite omnipresent in nature, and it's quite pictorially present. So we have seen that we have got the bell shaped curve, and reject percentage is 2.5, which is mentioned by the shaded area, which is at both the sides, that is in negative manner and in the positive manner at the x-axis. And when you see this accepted region is 95%, this we have already covered, which is usually called the intervals also. In interval and estimations, we have already talked about all those things. And acceptance is 95% in both the case. And if you see the critical value, rejection value region is this, critical value is this, and non-rejection region is this. So, and mu is this. So this is the thing by which we are going to interpret the whatever we have. So measuring effect size. So hypothesis test evaluates the statistical significance of the results from a research study. That is, the test determines whether or not it is likely that the obtained sample mean occurred without any contribution from a treatment effect. The hypothesis test is influenced not only by the size of the treatment effect but also by the size of the sample. Thus, even a very small effect can be significant if it is observed in a very large sample. So, measuring effect size. So because a significant effect does not necessarily mean a large effect, it is recommended that the hypothesis test be accompanied by a measure of the effect size, and we are going to use Cohen, that is standard deviation, as a standardized measure of effect size. Much like a z-score, Cohen is equal to standard deviation measures the size of the mean difference in terms of the standard deviation. So power of hypothesis, if we are going to talk about power of hypothesis thesis. The power of hypothesis test is defined is the probability that the test will reject the null hypothesis when the treatment does not have an effect. The power of a test depends on a variety of factors, including the size of the treatment effect and the size of the sample. So if we talk about research and null hypothesis, one tail specifies the hypothesized direction, and research hypothesis is denoted by H1, that is mu2 is greater than mu1, or mu2 minus mu1 is greater than 0. And if you talk about the null hypothesis, which is denoted by HO, and mu2 equals to mu1 or mu2 minus mu1 equals to 0. This is called one tail specifies the hypothesized direction, and we are going to talk about one tail test and two tail test in our coming presentation. So two tail direction is not specified, more common. Research hypothesis is H1, mu2 is unequal to mu1, or mu2 minus mu1 is unequal to 0. And if you talk about the null hypothesis, It's denoted by HO. Mu2 is equals to mu1 or mu2 minus mu1 equals to 0. So errors in hypothesis test just because the sample mean following treatment is different from the original population mean does not necessarily indicate that the treatment has caused a change. And you should recall that there is usually some discrepancy between the sample mean and the population mean simply as a result of a sampling error. So error in hypothesis test, because the hypothesis test relies on sample data and because sample data are not complementary reliable, there is always a risk that misleading data will cause the hypothesis test to reach a wrong conclusion. So two types of error are possible, that is type 1 error and type 2 error. We have a very elaborative sessions with the help of some real life scenarios example in our coming presentations where we are going to talk about type 1 errors and type 2 errors. So a type 1 error occurs when the sample data appears to show a treatment effect when in fact there is none, and in the case the researcher will reject the null hypothesis and falsely conclude that the treatment has an effect. Type 1 errors are caused by unusual, unrepresentative samples. Just by the chance the researchers select an extreme sample with the result that sample falls in the critical region even though the treatment has no effect. The hypothesis test is structured so that type 1 errors are very unlikely. Specifically, the probability of a type 1 error is equal to the alpha level. So if you talk about the type 2 level, a type 2 error occurs when the sample does not appear to have been affected by the treatment, when in fact the treatment does not have an effect. In this case, the researcher will fail to reject the null hypothesis and falsely conclude that the treatment does not have an effect. So type 2 errors are commonly the results of a very small treatment effect. Although the treatment does not have an effect, it is not large enough to show up in the research study. So if you see this particular matrix where actual situations are there, no effect, null hypothesis true, or effect exists when hypothesis false, and reject hypothesis null and retain hypothesis null. So what we have seen that type 1 error comes when there is no effect in null hypothesis and no effect and null hypothesis considered to be true, and or we have reject the null hypothesis, so type 1 error is there. And if you talk about the type 2 error exists when effects exist and null hypothesis is false and we have to retain the null hypothesis. So this is called type 2 error. So and decision is correct in both the cases, so that is why we are not affecting this. But this is very important, that is type 1 and type 2 error occurs when you are going to make experimental decisions. So level of significance is something which is going to be quite important in any test procedures. Both the types of errors should be kept minimum. They are interrelated. It is not possible to minimize both the errors simultaneously. Hence, in practice, the probability of type 1 error is fixed and type 2 error is minimized. The fixed value of type 1 error is called level of significance and is denoted by alpha. Thus, level of significance is the probability of rejecting a hypothesis might to be accepted, and most commonly used are 5% and 1%. And when decision is taken as a 5%, it means that 5 cases out of 100 is likely to reject a hypothesis which might to be accepted. Our decision to reject null hypothesis is 95% correct. So level of significance, traditionally we try to set type 1 error as 0.5 or 0.1, as in there is only a 5 or 1 in 100 chance that the variation that we are seeing is due to the chance. So this is called the level of significance. Again, there is no guarantee that 5 in 100 is rare enough, so significance level need to be chosen carefully. So multiple hypothesis testing in statistics is very important, because multiple testing refers to the potential increase in type 1 error that occurs when statistical tests are used repeatedly. For example, while doing multiple comparison to test null hypothesis, stating that the averages of several disjoint populations are equal to each other homogeneous. Intuitively, even if a particular outcome of an experiment is very unlikely to happen, the fact that the experiment is repeated multiple times will increase the probability that the outcome appears at least once. Or as an example, if a coin is tossed 10 times and lands 10 times on tail, it will usually be considered evidence that the coin is biased, because the probability of observing such a series is very low for a fair coin, that is 2 minus 10 is more or less equal to 10 minus 3. So however, if the same series of 10 tails in row appears as part of 10,000 tosses with the same coin, it is more likely to be seen as a random fluctuation in the long series of tosses. So now the time had come where we are going to talk about winding up this what we have recapitulated in this particular session, which was more emphasizing on theories of testing of hypotheses, and we have used certain jargons or terms which can be useful in the coming sessions, because we are having a dedicated session which can talk about the one tail test or two tail test, or type 1 error or type 2 error, or the t test, f test. So but this particular session was more emphasizing on the cut-in result to the theory of testing hypothesis. So theoretically, when you test a null hypothesis versus an alternative hypothesis, each hypothesis corresponds to a separate sampling distribution, and when you do a hypothesis test, you never know which distribution produces the results. You work with a sample mean, a point on the horizontal axis. It's your job to decide which distribution the sample mean is part of. You set up a critical value, a decision criterion. If the sample mean is on one side of the critical value, reject null hypothesis. If not, you don't. So that's all about this particular session is talking about, and we are going to talk more about the particular test which I have got a quite utility in the testing of hypothesis in our forthcoming session. Thank you very much.